Welcome back. So last time we talked about the framework of machine learning. We talked about forming a training problem during which we aim to minimize the average loss over the training data. We also talked about population loss, right? Essentially, the measure we use to assess whether the solution we learn during the training is going to perform well on new unseen data. Okay, and population loss was nothing but the loss over the average loss over the entire universe. Okay, we called basically the training problem as the empirical risk minimization problem. And the reason for that is that during the training, we basically form an empirical approximation of the population loss. Now we want to see how good is solving ERM. Okay, essentially how good is training. Right? So how good is the model we learned during the training in terms of performing on unseen data? So how generalizable the patterns that we learned during the training are. But one catch is that the ERM problem itself cannot be solved exactly in many cases. And that's especially true when we talk about deep learning models, optimizing deep learning models. So we're going to talk about some sorts of errors here that determine how good our learning is going to be. Okay? So let's talk about some notation. So let W hat be an approximate or suboptimal solution to the empirical risk minimization problem. So this is basically what you expect to learn when you optimize your deep learning model. Okay? So this is the base of the deep learning model that you're going to find after training is complete. Okay. Now let W bar and W star be the minimizers of the population loss, the average loss over the entire universe that obviously we cannot have access to, and the empirical loss that we have access to, right? So this is the loss we form by looking at our training data. Now, what do we need in order to assess the learning is good? So we need to bound this quantity. So this is essentially the population loss of the model that we learn suboptimally by solving the training problem suboptimally. So that's basically F bar evaluated at W hat minus the performance of the model that we could have learned if we had access to the population loss. So in some sense, you can imagine that this is best thing we could do, right? So if we had access to the population loss, that we obviously don't. Okay. So this is like a learning gap that we want to bound. Okay. Now, in many cases, to bound an error term, so you can think of it as an error term or a quantity of interest. What we do, we add and subtract certain quantities, if you will, to relate this quantity of interest to some tangible concepts. Okay, so in particular to some error terms that we have potentially a better understanding of. To do that here, so please bear with me, we in particular are going to add and subtract 3 terms. Okay, so these terms are the performance of my suboptimal model on the empirical loss, the performance of the models, the optimizer of the empirical loss, and finally the performance of the optimizer of the population loss on the empirical loss. Okay. But the merit of the story is that after you add and subtract these terms, the estimation error that we aim to bound is going to be sort of upper bounded by certain terms. Okay. So the first term is this. So again, F is our empirical loss. So the first term is nothing but essentially how well we do during our optimization process. So this is called the optimization error, okay? Because this just says that how well your suboptimal solution W hat is compared to the optimal solution W star, okay? The second term, if you look at it, for a fixed solution W hat, it is comparing the empirical loss and the population loss. Therefore, this is called the empirical approximation error. Empirical approximation error. Because this essentially says that how well your training data, your empirical training data, can represent the entire universe for all models W hat. Okay? Similarly, the third term is also related to empirical approximation error. Because again, I'm comparing the empirical loss F and the population loss F bar, but instead of evaluating their difference at W hat, I'm evaluating that on some other model, W star, okay? So if I had, if I knew that the empirical approximation error is bounded for all W, I could be able to bound both term 2 and term 3, okay? All right, so term 1, basically the optimization error. Term 2 and term 3 are related to the empirical approximation error. And let's talk about the third term, the last term, okay? So here I have F, the population loss evaluated at W star, minus, the empirical loss evaluated at W star, minus the empirical loss evaluated at W bar, okay? So let's recall what are W star and W bar, okay? So W star is nothing but the minimizer of F, and W bar is the minimizer of F bar, okay? Now here I'm evaluating them on F, okay? So because W star is the minimizer of F, it must be that the value of F at W star is less than all other W's. In particular, this is less than the loss of W bar. Therefore, this last term is non-positive, okay? So sometimes it's useful to get rid of non-positive terms, non-positive error terms, and this is an example of a case that I'm dropping this term. So in particular, you can safely remove this term, right? Okay. So therefore, what's the outcome of this analysis? This analysis says that the estimation error, which is essentially our way of characterizing how good the model that we learn, if we suboptimally solve the training problem, is going to be bounded by basically two terms. The first term is optimization error, how well you can solve the empirical risk minimization problem, how well you can perform the training step, and empirical approximation error, how well your training data can represent the entire universe, okay? Now, these two error terms can be controlled by better training algorithms and also having access to better or larger data sets, okay? So in particular, it is intuitive to see that if I have better algorithms that can solve the training problem faster and sooner, and potentially find higher quality solutions, I can reduce the optimization error. And similarly, if I have training algorithms, right, that can leverage the data better, or if I have access to more data points, I should be able to get a better approximation, empirical approximation to the population loss. So therefore, I should be able to control the last term. All right, so we talked about basically the estimation error. We talked about the optimization error and also the empirical approximation error. However, all of this is dependent upon which parametric model we are using to learn the relationship between the features and labels. In particular, if the models that we are leveraging have a very high capacity, they are very powerful, they should be able to represent very complex relationships between features and labels. Okay, so we should expect better learning performance. On the other hand, if our model is very simple, it's not powerful, it may not be able to learn the complicated relationship between the features and labels, despite having access to very advanced training algorithms, despite having access to a large amount of data, high quality data. Okay, so this is another source of error, therefore, representation error. Okay, so let's again recall our notation. W bar was the minimizer of the population loss, the average loss over the entire universe. And what we assume is that there exists this unknown relationships, A star, between the features and labels. Okay. As I mentioned, if our model is not powerful enough, even by minimizing the population loss, even if I had access to the entire universe, we may not be able to fully learn the relationship between the features and labels. Mathematically, that means that A star and our parametric model, when using W bar, are not necessarily the same. Okay, that depends on how powerful our parametric models are. Okay, and this leads to the representation error that we define by the difference between F bar at W bar and let's say some quantity that I denoted by F opt. And F opt, you can think of it as the loss if we knew the true relation. And many times we can assume that F bar is 0 or approximately 0. Okay, so basically this discussion can be demonstrated by the following figure. So let's assume that this is some A star, the true relationship between the features and labels that I want to learn. Okay, now this is the entire class of functions A, W that I'm leveraging during the training process. Now, this distance is nothing but the representation error. Okay? In this case, my model is not powerful enough. Therefore, regardless of how well I do during the training, regardless of how much data points I have access to, I'm not going to be able to reduce this error. Okay? Because the family of the parametric model that I'm leveraging does not include A star at all. Okay. On the other hand, if I had access to, let's say, another class of functions, let's denote that by A tilde. This is now a much more powerful class. So it does include A star in it. Therefore, I'm not going to have any representation error here in this example. And if I have access to better training algorithms, if I have access to an adequate number of data points, I should be able to perform very well. So the learning is going to be very, very successful. All right. Now this representation error can be controlled. So we've had this observation in practice, and we also have some theoretical understanding of that. As our deep learning models become deeper and wider, they tend to become more powerful. So that means that the representation error is going to go down. All right. So in summary, there are three important sources of error during the learning process. So the total learning error, if you will, is basically the sum of the representation error, how powerful our models are, our deep learning models are, in terms of capturing the relationships or arbitrary relationships, if you will. Optimization or training error, how good our algorithms are in terms of minimizing the empirical loss. And finally, empirical approximation error. Okay. Basically, how good our data is in terms of representing the universe of all data points. And these are source of errors, as I mentioned, that hopefully we can control by designing more powerful, more advanced models, by designing more advanced training algorithms that can leverage the data better. So in the next lecture, we're going to talk about a few simple examples of machine learning problems to solidify these concepts. Thank you.